Okay, today we will introduce some part about fast Fourier transform. And we can see that as a spectrum for original earthquake, we can get some curves like the blue one. And however, for a design earthquake wave, if we calculate their response spectrum, we'll see it look like this. Why they have different looks? Because for design purpose, we will fit the earthquake waveform so we can get a response spectrum that following or design spectrum. Design spectrum is basically decided by the past largest earthquake in the history and some seismic engineering, earthquake engineering experience. So for original waveform, we calculated, we measured on the site of after some earthquake, during some earthquake, we'll find that they will have not very certain, not very even spectrum like the design spectrum. However, for the design purpose, we will like the earthquake wave we're using for analysis that has a lot of power to make structure destroyed and collapse, so we can design structure safely. So today we will learn how to make a design spectrum fitted earthquake waves. Basically, if we have a few of this kind of sine wave, each of them have amplitude of 1 but have different frequency. If we plot them together, we can get sum them together, just simply sum them together, we can get this kind of earthquake wave. Okay, you can still see the basic forming of the wave here, but in each second's value, there will be this one plus this one plus this one plus this one equals this value. Okay, for this value plus this value plus this value plus this value, and get this value. So continually, waveform they will look like this. And also, we realize that they have different frequency, right? This is omega equals 1, this is omega equals 2, omega equals 3, omega equals 4. For lower frequency, you can see longer period, and for larger frequency, they have more even wave. Sorry, this is number 1, 2. Okay, waveform like this. And also we get the amplitude of 1 or 1 together. However, what if I have different amplitude? First is 1, second is 0.5, third is 0.2, fourth is 0.1. It means that this value is still 1, this value will multiple 0.2, 0.5, 0.1. And then we'll get some waveform that looks like this, which is different with the past thing we didn't have. Okay, if we write them to the equation, we'll get hxi will because ai 1, 0.5, 2, 0.1, and we'll sum them together, right? So also this equation we can also put a phase angle, means that with phase angle, if the phase angle starts from 0, then sine wave will start from 0, right? Phase angle is 0. If we have phase angle that is 0.5 pi, right? Then it will be. Oh, let me take off. Turn off the time. Okay. So if we start from 0.5 pi, you can see start from 1. So the starting point timing will be changed if the phi is different. It's marking the in-start value from there, but still they are periodically changed like a sine wave. However, start point is different. This is a phase angle, and if we change phase angle still, we can see that waveform again they changed greatly. Okay, so what is spectrum? Basically, Fourier spectrum is we're using fast Fourier spectrum, fast Fourier transform, or some transform for this kind of waveform that we know that this is a series sum of series sine or cosine wave with frequency with amplitude and with phase angle. For phase angle or amplitude, we can get, we know that they are sum of like this, which is different CI, and we can make a list with number I component with a different frequency and with different amplitude. And draw relationship of frequency and amplitude, we can get this kind of spectrum: 1, 0.5, 0.2, 0.1. Okay, so for different waveform, because their component the amplitude is different, so we can get different spectrum like this. This is just for a very simple case. However, for earthquake wave such like this, how can we know what is the CI amplitude of each component for each I number of the component? Is a problem we need to consider. Okay, so basically we have this kind of time series of y, which from y0 to yn, which is a series of data with time interval of delta t. And for each time, we know that is t is equals to n delta t, and it will become the sum of all these cosine and sine waves, a lot of sine and cosine wave. If we read in a sum style, then we can say that is from A0, which is from AI, BI. Each of them will have I and number of n. N is marking the time, I is marking the I component with number I also marking the different angular frequency here. And how can we decide AK, AI, BI for each I component, A0? We can use defining J, which is yn minus f. Yn is original data, fn is a result that we're using this series of x and y and sine and cosine waves. And we can for each AK number, right now we're using number k to instead of I. For each parameter AK, that we will find a very good value for AK, such the arrow J, square arrow J, becomes the least one. Okay, so which means their difference will become 0. It will be the least square arrow of these equations for AK. Okay, so if we expand this equation, it will be very long equation here. But today we will not explain all of this in a very short time. But we will let you know that after clear all the equations, we'll find a very easy way to find this series of AK and A0. Okay, so this time we don't need to remember all the equations. All equations is in the printout in the note. Okay, here we just want to know that finally A0 will become the average of AN multiple 2. Okay, so AK will be the 2 times of N multiple the sum of AY with a cosine of Kn. Okay, for each component of them, same as BK as this one. This is the Fourier transform. This is the Fourier's way to find out the frequency domain amplitude AK, BK by this equation. Okay, so if we use AK and BK A0 to calculate the FT, and then we can see that we transform from the frequency domain component AK, BK back to the time domain series of y, y1, y2, y3, go back to the equation FT like this. We call this inverse Fourier transform. Okay, or we can say using AK multiple cosine omega kt plus phi k, which because we combine this cosine and sine component together. Remember the lecture 4 when we introduced about structural damping, we already explained is using the Euler's equation, right? Here, ck will be the akbk's square root, and which cos phi k is a phase angle, which using the ak divided by ck to design cosine, and bk divided by ck to the sine phi k. And we also get omega k equals to this value. Take a very detailed look about this value. We can find that here k is number of the frequency, right? If the number k increase, then omega k increase. That means in the small number is a low frequency component. For k is going to going up and going larger and larger, then it becomes high frequency domain. Okay, for smaller k, ak, bk markings of low frequency domains amplitude, and for k is larger than ak, bk marking or ck marking the amplitude of high frequency domain. So we call this part 2 pi divided n delta t as a basic frequency, with the smallest frequency that we can measure. What the how small it is depending on number of data and delta t. Actually, so that means that is the total measuring time, duration time. So if we have a longer duration time, we have a smaller basic frequency, or we say that is a resolution of our spectrum that we can look at. So how small we can separate this waveform to a spectrum in the frequency domain, that is decided by omega 1, which also the duration time. Okay, so go back to how to adjust the response spectrum. So right now we can get a response spectrum for the period tk from to sak by the knowledge we know by Newmark beta method. We already explained it last time. And we also have a target response spectrum, which is designed by seismic design specification or code. And what do we need to do? Just compare them. For the TK component, we know the ratio of target and or recent the current response spectrum. Right now, we know a value of gamma k. If gamma k is larger than 1, that means the target response is larger, and the current waveform have a lower response than the design code, right? So we need to amplify these frequencies amplitude in the original wave to get an updated wave so that they can be nearer to the design spectrum. So SDR have a almost linear relationship between the amplitude to the component we have. So we use a very simple equation to update our AK and BK like this. Okay, and after update them, we just using the equation of inverse Fourier transform, go back to the original for the updated waveform, and then calculate the response spectrum again, and compare again, update again, and compare again, and inverse transform and response spectrum, compare again. This kind of cyclic we're going to do. Then we can get a very, very accurate response spectrum that exactly same with the design spectrum, almost exact same with the spectrum, in where the gamma k is very, very small. Okay, so when we're using the Fast Fourier Transform FFT in MATLAB, we will having a demo later, and we will know that in the MATLAB we don't need to write that complicated equations. We just using very simple function FFT, just like this. So y is original wave here, and NFFT is the number to get the Fourier transform. Here, if the number of the data is a power of 2, then the Fourier transform will be very, very fast. So generally, if we have a waveform number of 3,000 or 4,000, we'll change them to 4096. And in the demo, we will know that we can get this number by getting the nearest power of 2. So we can get this number of 4092 from 4000 or 3000 waveform. By just zero padding them later. We don't need to do that, it will do it automatically for us. Okay, so after Fourier transform, we'll get a vector of y, which is a Fourier transformed frequency domain component of y. So what is the inside structure of the y? We will see it in the demonstration, but we will know that y in the first component of y is a constant component, A0. Okay, you don't have imaginary part. Imaginary part is equal to 0. You only have the constant part is A0. Okay, or we say this is the half of the average of all waveform. And from the second number for y is the number 1 component, k equals to 1. Okay, so number 2 is number 1 in the Fourier transform. So that is a k plus 1 component in y that marking the k component. And also n divided by 2 plus 1 component will be again another constant component b0 half. And after that, from half n plus 1, from half n plus 2 will be the conjunction part of number half n component with the y equals n plus half n component. Okay, so finally we will know that for this k component, the positive component, one part of them is in yk plus 1. Their conjunction part, conjunction part means the imaginary part's number its direction is inversed. Okay, so if you plus 2 conjunction part, that only in the AK will result it. Okay, if you multiply them, it will becomes the square of their total length in the both real and imaginary part. So for one part is in the k plus 1 location, and their conjunction part is n plus 1 minus k location inside the y vector. Okay, so you need to, for k component, you need to update both this component and their conjunction component, or you cannot inversely transform back to the waveform successfully. If you didn't, if you get the number wrong, when you do the inverse transform, you will get a result that with real and imaginary part, and your waveform will be very, very strange. So if you, when you programming it, if you see your waveform becomes very, very strange, then you need to go back to check if their inversely transformed waveform is only real number. If that is not only real number, you have imaginary number, that means that maybe you have a wrong setting of the number when you do the program. Okay, please check about this. And if you do the design, if you look at the design spectrum for Japan's design spectrum, you will find this kind of equation easily. And for calculation this kind of spectrum for each ti, you just need this kind of function that you just do in your program. Okay, for each t is a spectrum, a vector, right? For you just do the for loop for them. If they're smaller than that, if it's smaller than that, if it's smaller than that, using the 3 equations to calculate SAI and get them back. Okay, so basic routine for how to design, so to get a spectrum fitted waveform is, firstly, you need input the waveform. Okay. Secondly, you need setting the interest period, such as 0.1 to 10 seconds. We just want to get the in this range, we will get fitted with design spectrum. Other range, we will set them to 0, or we just ignore them this time. Okay. So for the Fourier transform, using Fourier transform, we get y, which is the frequency domain component, and also calculate the tk in the range of 0.1 to 10. Okay, so we'll find which number of k for tk is about 0.1. Okay, so you only calculate inversely transform later this part back to waveform, right? And then we will set in the Z spectrum range, and inside this range, TKS to TKN for the T spectrum, which is inside 0.1 to 10. And then we will calculate response spectrum in TKS and TKN. S means start, E means end. Okay, why we calculate this part? Because response spectrum is very time consuming. Okay, so if we calculate a lot of that, it will take a lot of time, so we just take some part of the time. And compare design and response spectrum, and then you get gamma k for each component. Then update it AK, BK by gamma k by the method we explained before. Just here, for k component, we know that it's k plus 1, right? So you need multiple gamma k to y component k plus 1 for each k. Okay, and don't forget also that the y n plus 1 minus k component with the conjunction component number k, that equals to the conjunction of y k plus 1, right, which is updated. Then you can inverse transform them back to the waveform, then get the updated wave. Okay, this is how do we get updated wave as we examined before. So go back to this step cyclically until you can get a design waveform that you wanted.